Welcome to the second lecture in EE404. In this second lecture, we are first going to see the definition of linearity. So the course is about nonlinear systems. So why do we learn about linearity? Because nonlinearity is usually defined by the lack of linearity. That is why in order to be able to understand nonlinearity, we have to know first, in terms of a system, what linearity would mean. So let us start. So the first thing that we are going to do is to define linearity. So I'm going to define what a linear system is. In general, we know what a linear relationship is, and that is y is equal to ax type of equation. But in terms of a system, linearity is much more complicated. So suppose that I consider an abstract system. So this is an nth order system. And it has an input, u, and it has an output, y. Okay? And in general, the systems that we consider, they are going to have a state vector, and this nth order system defines the number of states in the system. In order to be able to represent that system, I would need n state variables. And as a result, the system would also be dependent on some initial conditions. So there would be n initial conditions. These would form a vector x0, and this denotes the initial state. Okay? Then the output of this system is a function of several quantities. This is an abstract system, and I would like to form the output of this system as a function of its input, initial state, and time. The first thing that the output is a function of is time. So output is a function of time, and the output is also a function of the initial condition, x0, and the output is also a function of the input. Okay? So I have u here. Okay? So when I try to show the whole input function or any whole function, I use this notation, function name and parentheses and a dot. This shows the function as a whole. If I substitute some value inside this parentheses, then that would mean the value of that function at that specific time instant, or at that specific argument value. So in general, the output is a function of time, initial state, and the input. And the linearity is actually, it can be defined in terms of such a representation, such an abstract representation. So let us write this. The system, whatever the name of the system is said to be linear if and only if. I will show if and only if with the letters IFF. You won't believe me, but that is my F. Okay, double F here. So the system is said to be linear if and only if the following properties are satisfied. So there are three properties that needs to be satisfied for a system to be linear. Let us write the first property. I will write the properties in terms of this generic output here. So I'm going to write this. So y of t, and I have x0 and u, can be decomposed into two functions. Okay? So this is going to be y of t x0 and the function 0 plus the function y, t, and I have 0 initial condition and the effect of the input here. Okay? So you see that I have written an arbitrary output of this function as the sum of two individual outputs. Okay? The first individual output would correspond to this initial condition and with zero input. Okay, this denotes the zero function. Okay, and the second term denotes the output of the system for zero initial conditions and with the input u. Okay, so what does this property mean? It means that for a linear system, I can decompose the effect of the initial condition and the effect of the input from in the output. Okay, so this is the decomposition. We can decompose any output of a system into two parts. In one of them, I have zero input, and in the other one, I have zero initial conditions. Okay, this property has a in the past, you might have seen such properties, especially in circuit theory, for example. And this type of response of the system is called the zero input response. And this type of response is called zero state response. And in a linear system, we can always decompose an arbitrary output into two parts, zero input part and zero state part. Effects of the initial condition can be decomposed from the effects of the input, and that is what this property means in a linear system. The second property is going to be about the effect of the input here. Okay? Suppose that I look at the zero state response of the system for an input which is a linear combination u1 of t plus alpha 2 u2 of t. Okay? I am now concentrating only on the zero state response of the system. Okay? And I look at the response that I would get for zero initial state and a linear combination of some input functions. Okay? For a linear system, the response of the linear system would be equal to alpha 1 y t0 u1. Well, let me put here my dots so I don't want to specify a time instant, u1 plus alpha 2 y t0, and I have u2 here. Okay? So for a linear system, if with the zero initial conditions, if I give the system a linear combination of some inputs, the output of this system to that input would be the linear combination of the outputs that I would obtain if I give these inputs to the system individually. Okay? And from such a property, we can actually extract really lots of different properties. All right? So the first thing that I can extract would be the following. Okay? So I would have the following selection. Let us say alpha 1 is equal to alpha, and let us say alpha 2 is equal to 0. Okay? Then, of course, this is true for any alpha. Okay? This is true for all alpha 1, alpha 2, for all u1 and u2 that I can give the system. Similarly, this first property should be correct. So it is not only sufficient for a system to be linear that this property is satisfied for a single initial condition and the input. It should be satisfied for all x0 in Rn and for all input functions. Okay? So I should not forget here these for all conditions. So now definitely if this property is satisfied for all alpha 1, alpha 2, and for all u1 and u2, I can actually select alpha 1 equals to alpha, and I can select alpha 2 equals to 0. Okay? Let me select u1 is equal to u, and another function, and let us say u2, suppose that I choose it to be equal to 0. Okay? With these selections, I would have the following: y of t 0, and this would be alpha u plus 0 times 0. So this would be alpha times u. Okay? And that is equal to alpha 1 is alpha y t0 u. Okay? And this term is equal to 0 because alpha 2 is equal to 0. All right? So what does this property tell us? So we see here that for a linear system, if I scale its input with 0 initial conditions, the output is going to be scaled as well. Okay, with the same scaling coefficient. So if I give the system input u of t, and if I get the output y of t from a linear system, Ls, then if I give the system alpha u of t, then the linear system would give me alpha yt. Okay? So if I scale the input when I have 0 initial conditions, the output would be scaled as well with the same coefficient. This property is called the scaling property of a linear system. So I can actually get another property, I can derive another property from this single property. And in order to be able to do that, I will make the following selection. Alpha 1 is equal to alpha 2 equals to 1. Let us choose both of the coefficients to be 1. And then what is going to happen to this property? Y of t0 u1 plus u2 is equal to y of t 0 u1 plus y of t 0 u2. Okay? So in a linear system, if I give this summation of the inputs to the system with 0 initial conditions, the output would be the summation of the individual outputs that I would get if I gave this system these input functions individually. Okay? So this is also a very familiar, it must be a familiar rule for linear systems, and this is about the following fact. So if I have u1 of t and if I have u2 of t, if I sum them and when I give them to the system, okay, this is the linear system, then I would get y. Okay, there is a summation here. Here I have the summation u1 plus u2, and I give this to the system and I get the response. This is this thing. Okay, 0 initial conditions, and I give the summation of the inputs to the system and I get the output. This is equivalent to the following. If I give the system the input u1 individually, okay, then I get an output here. This is this thing. And if I give the system u2 and I get another output here, if I sum them, this is also going to be y. Okay? The outputs here and here would be equal. So I have the linear system can be changed, can be interchanged with the summation. That is the rule. Okay? Here I exchange the summation operation with the linear system, and no change happens in the output. Okay? And this property is called, in system theory, if you must also have heard this in circuit theory courses, principle of superposition. If I superpose the inputs, then the individual outputs to these individual inputs would be superposed. Okay? They are summed. And you see that this is true for zero initial conditions. If the system had a non-zero initial condition, such a property might not hold. Look at this property. There are zero initial conditions in all parts here. In this property, zero initial conditions. Okay? The third and the last property is going to be the following. The same thing, the same type of idea can be applied on initial conditions. Okay? When I have zero input response, I will set the inputs to zero, but in this case I'm going to get a linear combination of initial conditions here, and the response is going to be the same linear combination with the individual initial conditions given to the system. Okay, that is the third property of linearity. So I have y of t. Now instead of the zero initial condition, I will have this: alpha 1 x0 1 plus alpha 2 x0 2, and I would have zero input to the system. So that is going to be equal to y. So I will have alpha 1 yt x0 1 and 0 input plus alpha 2 yt x0 2 and 0 input here. Okay? So this is the third property, and this should be correct for all x01, x02 in Rn, and that should be correct for all alpha scalars, alpha 1, alpha 2. All right? So from this one you can also generate some other conditions. Let us look at them. So I can make a similar selections. So alpha 1 is equal to alpha 2 equals to 0, x01 is equal to x0, and x02 is equal to just 0. Okay? In that case, I can actually show that y of t alpha x0, 0 input, is equal to alpha y of t x0, 0. So when a linear system gets 0 input, then scaling the initial condition would scale the overall response. Okay? If you scale the initial condition, then the response would be scaled with the same scaling constant. And B would be the following. So alpha 1 equals to alpha 2 equals to 1. In that case, I would have the property yt. So I have x01 plus x02 with 0 input. That is equal to y of t x01, 0 input, plus y of t x02, 0 input. When a linear system gets 0 input, then if you start the system at the sum of two initial conditions, then the response would be the sum of the responses when the system is started individually with these initial conditions. Okay? So that is the final property that we can get from these. Right? So in general you have three main properties, and these two properties we have derived from the individual properties there. Okay? So the first property tells us that the effect of the initial condition can be decomposed or can be separated from the effect of the input. Okay? That is a decomposition into zero input response and the response, zero state response of a system. The second property is the linearity of the zero state response. Okay? This tells me that zero state response is linear with respect to these inputs. If you give the system zero initial condition, and if you give the system an input, which is a linear combination of some input functions, the output would be the same linear combination of some individual outputs when the system is given with these individual input functions. Similarly, the final one is the linearity of the system with respect to its initial conditions. Okay? So of course, in this case, this is the linearity of zero input response. Okay? Because in all of the outputs here, you have zero input. And this tells me that the zero input response, if you started with a linear combination of some initial conditions, the output would be the same linear combination of zero input responses when the system is initialized with these individual initial conditions. Okay? So these are the properties of a linear system, and they are quite powerful properties. Okay? So linearity, therefore, is really an exception in system theory. Nonlinearity is the common theme, and linearity is really a very, very specific condition that a system can have. So because these responses, these properties are really powerful, if we have a linear system, then we can really say a lot of things about that system by making a small number of experiments on that system. So now we're going to solve an example related to that concept. Let us say example. Four measurements are made on a linear system. I'm going to make a table here. So I will first tell you what the input is in the experiment and what the initial condition is and what the output is for that initial condition and input pair. So if the input is sine t and if the initial condition is 0, 0, then I collect this at the end of the experiment, and I here write y1 of t. So I give the system the input sine of t, and I give the system 0 initial condition, and I collect a waveform, y1 of t, at the end of the experiment. That is my measurement, y1 of t. Okay? And then the second experiment is this. Cosine t, still 0 initial condition, and the measurement that I collect is called y2 of t. It's a function of time. Maybe I sample it and then I collect it, I store it in a computer. Okay? So now the third experiment and fourth experiment would be related to zero inputs. I give the system zero input, but I start the system from the initial conditions 1, 0 and 0, 1. And the outputs that I collect for these cases would be called y3 of t and y4 of t. Okay? So now the task of the example is going to be the following. Find y of t in terms of y1 of t, y2 of t, y3 of t, and y4 of t when the input is, the initial condition is this, alpha, beta, some arbitrary numbers, alpha and beta, and the input is a cosine t plus phi. Okay? So we are given that the system is linear, and we are given the results of these 4 experiments. And we are wondering about the response of the system to this initial condition and to this input at the same time. Okay? And we would like to write this output in terms of the experimental outputs that we collected from the system using the linearity property. Okay? So the first thing that I'm going to do is going to be to separate the effect of the input from the effect of the initial condition. So we are wondering about this, y of t, and I have the initial condition alpha, beta, and I have the input a cosine t plus phi. Okay? We are wondering about this output of the system. And I need to write this in terms of these individual outputs, these experimental outputs that we have collected. All right? Now here is what I'm going to do. I'm first going to separate this output into zero state response and zero input response. So I have y of t, I would have alpha, beta, and here I have the input 0, because my experiments are either 0 input cases or 0 state cases. Okay? So I have plus y of t, and I have in this case 0 state, and finally a cosine t plus phi. Okay? So now I can work on these individual 0 input and 0 state outputs. The first thing that I'm going to see is that this initial condition can be written as a linear combination of these 2 initial conditions. So you see that in this output I have 0 input, and this initial condition can be written as a linear combination of these initial conditions. Okay? 0 input and these initial conditions. So I can write here this. Alpha beta is equal to alpha times 1, 0 plus beta times 0, 1. Okay? As a result, I can write this response as yt alpha beta 0 is equal to alpha times y t 1, 0, 0 input plus beta yt 0, 1, and I have 0 input. Okay? But what is this? This is the output of the system that we would get when I give the system this initial condition with 0 input. That is nothing but y3. Alpha times y3 of t plus, this is nothing but the output that I would get when I give the system 0 input and the initial condition 0, 1. So this is y4. Okay, so I have written this first term as a linear combination of y3 and y4. Now I will be working on this 0 state case. Okay, because and now I'm going to try to write that second output as a linear combination of y1 and y2. Okay, because these are 0 state cases as well, and I have two different inputs here, sine t and cosine t. In order to be able to do that, I will write this input as a linear combination of those individual inputs, sine t, cosine t. Okay? How can I do that? So I have a cosine t plus phi is equal to a times cosine t times cosine phi minus a sine t sine phi. Okay? Now I can actually write this as a cosine phi. This is like a coefficient to me, and that is cosine t minus a sine phi. This is another coefficient times sine t. So you see that this input that I give the system is a linear combination of these two inputs. Okay? Sine t and cosine t, and the coefficients of that linear combination is a cosine phi and a sine phi. All right. So now I can write this quantity here, y of t and 0 initial condition, and this linear combination of inputs. All right. That is going to be the same linear combination of the outputs, a cosine phi, times the output for this individual input, y t 0, 0 cosine t minus a sine phi times the output for sine of t. And that is going to be yt 0, 0 sine t. Okay? What about those outputs? This is the output of the system for 0 initial condition and cosine input. That is y2. So this is y2. A cosine phi y2 of t minus a sine phi, and this is going to be just y1 of t. Okay? Now all I have to do is to combine these results to write my final answer. So y of t is going to be first these things, alpha y3 plus beta y4. I am skipping t's here, and plus a cosine phi y2 minus a sine phi y1. Okay, that is my answer. And while trying to obtain this answer, we have obtained the linearity properties of that linear system. Which properties did I use? So here, for writing this first equation, I have used the first property, and for writing the second equation, this decomposition, I have used the linearity of the 0 input response, and for writing this last one, I used the linearity of the 0 state response, which was the second property. Okay? And that completes this example. So now we know what linearity is. And if any one of these properties that we gave for linearity, if any one of them is not satisfied, then we know that a system should be nonlinear. Okay? A linear system should satisfy all of these properties. So now let us look at the representations of nonlinear systems. So you might remember from the course EE404 that a system, dynamical system, might have different representations. In 302, which is a prerequisite of this course, 404, you have seen three representations. Okay? The first representation is called differential equation representation. The second representation is transfer function representation, and the third representation is called the state space representation. Okay? There are these three different representations which are somehow equivalent to each other. For nonlinear systems, unfortunately, we would lose one of these representations. Okay? And that is the transfer function representation. You know that a transfer function representation is nothing but a Laplace domain representation, and it is obtained by taking the Laplace transform of a differential equation or Laplace transform of a state space equation. Okay? So in general, a Laplace transform is a linear function. Okay? And it can be interchanged with other linear operators, but Laplace transform can never be interchanged with nonlinear operators. Okay? So for nonlinear systems, really we cannot use the Laplace transformation to obtain a representation for that system. Okay? So in general, a nonlinear system doesn't have any transfer function representation because Laplace transform cannot be used in obtaining a representation for a nonlinear system. Okay? So we lose one of the representations, and for nonlinear systems, we have two types of representations: differential equation and state space representation. So we know that transfer function was a Laplace domain and a frequency domain representation somehow. What about the other two representations? Differential equation and state space representations. They are in general time domain representations, okay? So a linear system has both time domain and Laplace domain representations. But for nonlinear systems, we only have the remaining two time domain representations, okay? So now let us try to look at what a state space representation would look like for a nonlinear system. I will first write a generic nonlinear state space representation. So x dot is equal to f of xu, and y is equal to g of xu. This is a general, so I can say that this is time invariant and forced state space representation for a nonlinear system. We are going to see what the types of state space representations for nonlinear systems would be quite soon. So here I have a nonlinear system in state space representation in general form. So we have in general a nonlinear function of x and u in the state equation, and we have a nonlinear function of state and the input in the output equation. Okay? Remember what the state space representation of a linear system would be looking like. It is just this: y is equal to cx plus du. This is a state space representation of a linear system, and in general, you can, instead of these linear multiplications and summations here, we can have any nonlinear function of input and the state in a nonlinear system. And similarly, in the output equation, we can have similar things. And here, we know that the dimension of the state, which is n in general, gives us the order of the system. Okay? So n is the order of the system. It is the same concept for both the linear system and the nonlinear system. And you see that this is a time domain representation. That is a differential equation that I write in time domain. So in this course, we're going to be mostly using this state space representation. Okay? So, but we know that there is another type of representation, which is a differential equation representation, that can be used to represent a nonlinear system. So in general, when we have a differential equation in this course, in order to be able to examine it, or in order to be able to use the tools that we derive, that we have to analyze that system, we are first going to convert it into a state space representation. Okay? So let us now look at what a differential equation representation of a nonlinear system would be looking like. Let me write here, an nth order nonlinear system can be described by an nth order ordinary nonlinear differential equation. In order to be able to write that representation, I'm going to define the following. Let us say that y of t is a scalar output. So we are going to be mainly concerned with SISO systems here, single input, single output systems. So y of t and u of t are scalars for our purposes. Okay? U of t is the scalar input. So I'm going to now write a nonlinear differential equation, but this is going to be still not the most general case. So there would be still some loss of generality in the differential equation that I write. So here I'm defining y to the nth order derivative t as follows. This is d to the n y of dt to the n of t. Okay? This shows, this parenthesized superscript would show the nth order derivative of a function of time. Okay? And I would have here, of course, the 0th order derivative just means no derivative at all. Okay? So I have here, this is y of t. All right? So now I'm going to write a nonlinear differential equation representation of a nonlinear system. And it's looking like this. H of y of t, y to the first order derivative of t. Sometimes I just write y prime of t here. It really shows the same thing. And y second order derivative of t, going until yn minus first order derivative of t, y of t, and I have u of t. Okay? So I told you that this is still not the most general form of a nonlinear differential equation. Okay? Why do you think is that? What is missing here? So in a most general nonlinear system or nonlinear differential equation, I would also have the higher order derivatives of the input I might have. Okay? So here I do not include those terms, and we are not going to be concerned of such systems in this course either. Okay? So here in a more general nonlinear differential equation, these inputs can have higher order derivatives inside the nonlinear function, but here we are not thinking about those. So in this course, when we encounter such a nonlinear differential equation like this, we are going to want to convert it into a state space representation like this. Okay? So then then we are going to investigate its properties on its state space representation. So how can we convert such a nonlinear differential equation into state space form? As you know, there are infinitely many such ways, and the infinitely many ways is coming because of what the state is can change. So remember, for a state space representation for a linear system, there is only a single transfer function representation. But for a single transfer function, there are infinitely many state space representations for linear systems. And the same thing is correct. So if you change the definition of your state vector, then the state space representations of nonlinear systems would change as well. Okay? So for a single nonlinear differential equation, there might be infinitely many state space representation. It all depends on the definition of your state variables. So remember, in linear systems, for a single transfer function, we can find controllable canonical form, observable canonical form, or diagonal canonical form type of representations. These are only 3 of the infinitely many possible ones. Okay? Here we are going to choose a very, very specific state space representations for such a nonlinear differential equation. Here this h is in general a nonlinear function of these arguments here. So if this is my nonlinear differential equation, what does a linear differential equation look like? You might remember that, right? So in that case, if the system is linear, so this is the nonlinear case. H can be a nonlinear function. Remember, in the linear case, the differential equation would look like this: a1y of t plus a2y1 of t plus a3y2 of t, going until an y n minus first order derivative of t plus b1 u of t. Okay? This is the linear version of this nonlinear differential equation. And as I told you, in general here, I might have additional coefficients like b2 u prime of t, b3 u double prime of t, etc. Okay? But here we are not thinking about such terms. So now let us define a state space representation for this nonlinear differential equation. So this is the linear case. So for defining a state space representation for that nonlinear differential equation, I'm going to define the following state vector. X is going to be, how many state variables do I have to use here? This was an nth order nonlinear system. Therefore, the number of state variables that I need to use here is just n. So I have x1, x2 going until xn here. And here I'm defining the following state variables. x1 is y of t, x2 is y prime of t, x3 is y double prime of t, and I can continue with these definitions until xn, y n minus first order derivative of t. Okay? So these are my state variable definitions. Now I have to obtain this type of state space representation for this system. Okay? So what does a state space representation have? It has first a state equation, and in this state equation I need to express the first order derivatives of the state variables in terms of the state variables and the input. Okay? Let us try to do that. x1 dot, I need to express this x1 dot in terms of these state variables and the input. Okay? But you see that x1 dot is nothing but the first order derivative of y, which is the second state variable. Okay? So this is nothing but x2. And x2 dot is x2 is y prime, x2 dot is going to be y double prime, okay, which is x3. So this is going to continue until where? This is going to continue until the n minus first variable. xn minus 1 dot is going to be just xn. Okay? There are n minus 1 first order derivatives of the state variables here, and I have expressed them in terms of the state variables or input. The input doesn't appear at all in the first n minus first equation, in the first n minus 1 equations. Okay? What about the last equation? xn dot is equal to, in this case, xn dot is going to be the derivative of yn minus first order derivative of t. And therefore, this is going to be the derivative of this thing would be y to the nth order derivative of t, which is this thing. Okay? Y nth order derivative is given by this equation here. So that is where I am going to use my nonlinear differential equation. In the first n minus 1 equations, I didn't use the nonlinear differential equation at all. But in the last equation, I need to use it. Okay? So I have h, and I need to replace everything here, all arguments here, into either state variables or the input. Okay? Because x dot is equal to f of xu expresses everything here in terms of the state variables and the input. So I have I have y is x1, okay? And y prime is x2. So these are continuing until the n minus first order derivative. So I have xn here, and I would have the input u. Okay? So this is my state equation, and this is in the form x dot is equal to f of xu. Remember, f is a vector valued function, and it has as many functions as the number of state variables. So f is actually f1 of xu, f2 of xu, going until fn of xu. Okay? So we are seeing here that f1 of xu is x2. It is not dependent on u or other state variables other than x2 here. And only fn is dependent on all of the state variables and u here for this system. For the other functions here in f, they are linear functions of x and u. But this last function brings the nonlinearity to us. Okay? That is, if this function was also linear, like this linear differential equation here, then I would have ax plus bu here, and I can find a and b matrix and vector here. Okay? So this is the state equation part of the conversion. What about the output equation? And a differential equation has also, a state space representation has also the output equation. Okay? How can I obtain that? The output is y here, and in order to be able to write it, I need to obtain the output as a nonlinear function of x and u. And here you see that this output is nothing but the first state variable. Okay? So in this case, I have y is equal to x1 is my output equation. So when we try to convert such a differential equation into state space form, the first n-1 equations, they turn out to be linear. But the last equation of the state equation would be nonlinear, and the output equation would also be linear here. So in this case, I have g of xu is nothing but x1. Okay? So we are going to use this type of conversion when we encounter a nonlinear system. Of course, other types of states can be selected. For example, I can just reverse the order of the state variables here, and I can obtain a different state space representation. But this is the basic one. And if you need to convert, if you are not asked otherwise, you can use this type of conversion method for converting a nonlinear differential equation into a state space representation. Okay? So this actually concludes the second lecture. In the third lecture, we are going to see the types of nonlinear systems. So this is a generic state space representation, but we are going to show that there are more types that we can define. What is happening? What happens? What is the name of the system, for example, when we don't have any input in the system? We're going to see that we are going to have such different naming for nonlinear systems, and then we are going to see the important concept of an equilibrium point for a nonlinear system. But these are going to be for the third lecture. Thank you for watching. Bye-bye.